Okay, so good morning, everyone. I hope you can hear me. Um, I'm starting a new recording because there was an issue with the recording to yesterday's live session. But please do not worry, all the questions discussed will be the same, and the concept discussed will also be the same. So I'll try to follow the same format. I'll pretend as if there are people in this meeting, and then I will present to you all the questions. Okay, so yeah, starting with the beginning. Uh, my name is Bhavya. Okay, and I am a PhD scholar at IIT Madras, working in theoretical computer science. So I'll be doing live sessions for the discrete mathematics course on NPTEL, and my timings are Tuesdays. Okay, Tuesdays 6 p.m. to 8 p.m. There is another slot for live interaction on Mondays 6 p.m. to 8 p.m. But Suryadip Nath will be taking care of that. But I will be taking care of the live session specifically on this slot 6 p.m. to 8 p.m. every week. Okay. And what we do during the live sessions would be we pick a few problems, show you how to solve the problems. I would also revisit some concepts taught in the previous week, and then before embarking on the concepts. Right. So yeah. So let us begin with the topic of um, the week one, which is counting. Now, um, in discrete mathematics, we talk about what are called discrete things, discrete structures, discrete objects, which means simply things that you can, what you call, enumerate. You can count them, you can number them, and so on. So, if that is the case, one natural question that kind of arises is like, how do we count those objects? It seems like a pretty basic thing, but counting goes a long way. It is used all over in mathematics and all over in computer science. And counting can get pretty advanced, but all of them depend on what are called basic counting techniques. Okay, and basic counting techniques include your permutations, combinations, and these different methods like the bars method, stars and bars methods, ball and bins method, and so on. And you might have seen those counting techniques in the lecture videos of week one. So let us kind of revisit them before I start with solving the problems. So yeah, the first question here. Okay. Okay. Yeah. So the first question here is what is combination? Okay. So this is what is called combination. So we read this as n choose k. Okay. So n choose k, or we also denote it in brackets n choose k. Okay, in such brackets. What is n choose k? The formula is n factorial divided by k factorial times n minus k factorial. Okay, how this formula comes, I will not address, but it comes from, you can look at the week one recording, the week one lecture videos. Okay, but what it essentially means is I have a set of n objects. Okay, and from them I'm picking k objects. Okay, what I'm asking is how many ways there are to pick those objects. Okay, for example, let's say my set of n objects is 1, 2, 3, 4, 5. So what is n here? N is 5. We have 5 objects here. Correct. Now what we do is, let's say I have to pick 3 objects from here. K equals 3. Then I could do 1, 2, 3, or I could go. Yeah, so let's say 145. So 145 is another uh, set of objects of size 3. So what we want to count is how many of these sets are there. So that is exactly given by your n choose 3, or n written this way, n choose 3 in this way. So which is nothing but, now n is 5 for you here, right? And k is 3 here. So n choose 5 choose 3, which is by your formula here, right? We got 5 factorial divided by your 3 factorial, right? And n minus 5 factorial, which is nothing but 2 factorial. So further, you can cancel it out this way. 5 times 4 times 3 factorial, okay? And 3 factorial here times 2 factorial. And you can cancel out the 3 factorial and 3 factorial to give 5 times 4 is 20 divided by 2, which is equal to 10. So there are 10 ways in which you can select an object this way. This is what it signifies. Okay. So now, that we've talked about, combinations, okay, and the key idea here is about choosing here, right? I want to talk about what are called permutations, okay? So this is what is called a permutation. So a permutation can be denoted by P, okay, NPK. So NPK is defined in the following way: n factorial divided by n minus k factorial. Okay. So what does a permutation mean? A permutation, okay, is not just about selecting objects, not just about choosing objects. A permutation means first you select, so NPK means first select or choose k objects from n objects. Okay, first you do that. Then what you do, arrange those k objects. Okay, for example, I'm not only talking about this 1 2 3 2 3 4 and so on. Considering I'm considering, okay, it's not, let's use this notation. I'm considering 2 1 3 and 1 2 3 as separate objects. So I'm even counting the arrangements within them. So that is what I'm counting. Okay, we already know that there are 10 ways to choose them, but even after choose them, in how many ways can I arrange them within themselves? Okay, so that is what is denoted by permutation. So let's see if in this case when n is 5 and k is 3, how many arrangements are there? So 5 p3, okay, will be equal to 5 factorial, okay, which is your n factorial by the formula here, right? So 5 factorial divided by n minus k factorial. For us, k is 3 and n is 5, and 5 minus 3 is 2 factorial. Getting it? So how many ways are there? 5 times 4 times 3 times 2 factorial divided by 2 factorial. So when you cancel out 2 factorial and 2 factorial, what you get? 5 4s are 20. 20 times 3 is 60. So there are 60 ways to do this, to choose 3 objects and arrange them. Okay, that is all well and good. Now what we do is we look at what are called the sum rule and product rule. Often we encounter situations where directly we do not know. It is not simple as choosing 3 objects from 5 objects and so on. It is often it is a combination of several events. Okay, so let's say I count the number of ways that a certain event A happens. Okay, and I count the number of ways that B happens. And I ask this question: how many ways can there be such that A happens or B happens? Okay, and this is what is called the sum rule. Sum rule simply says that if I need to count the number of ways that A happens or B happens, okay, then I simply do the sum of those two events, right? So so you can imagine, like, how many ways are there that 4 people can be selected from. four people can be arranged, okay, from a set of five people, and in how many ways can three people be arranged in terms of five people, and how many ways can four people be arranged or three people arranged? Okay, then you can use this rule. Number of way that four people can be arranged plus number of ways that three people can be arranged. We'll see examples about this later. For now, remember this as a sum rule. The other case is the AND case. Okay, number of ways that event A happens and the number of ways that event B happens. Okay, and we know the number of ways that A and B happens for each of them. Okay, then what we can do, we can simply multiply those numbers, number of ways that A happens times the number of ways that B happens. Okay, and therefore it is called the product rule. Okay, now look here. So we'll try to solve the first question. The first question says the following: a box contains, okay, 12 black and 8 green marbles. Okay, how many ways can 3 black and 2 green marbles be chosen? That is the question. Now let us visualize it. So the question says 12 black. So let me write black marbles this way. Okay, 12 black marbles. Good. 8 green marbles. I have green here. So 1, 2, 3, 4, 5, 6, 7, 8. Okay. Okay. 8 green marbles. Now question is, how many ways can we pick 3 black marbles and 2 green marbles be chosen? Okay. So the first thing to ask about it is this a permutation problem or is it a combination problem? Think about it for a while. So the answer is that it is a combination problem. Why? Because the question is asking about choosing them. It is not asking about how we can arrange those marbles. If let's say the white marbles were numbered from 1 till 12 and green marbles were numbered from 1 till 8, and the arrangement, I'm asking about how you can arrange those marbles, pick 3 black marbles and arrange them and so on. If that was the question, then it would have been permutation. But since we are only asking about choosing those marbles, we don't care about those arrangements. So in that case, what we have is that we need to, this is a combination problem, combination question. Okay. So yeah. So let us look at the two events separately. Okay. How many ways, number of ways, okay. By this hash sign, I'm denoting the number of ways. Okay. The number of ways to choose, okay, 3 black marbles. The question is asking 3 black marbles out of how many marbles? 12 in total. Black marbles. Okay. The number of ways to choose 3 black marbles out of 12 black marbles is, by definition, we already know that this is 12 choose 3. Okay. We know this by definition. Next, we would simply want to simplify it. Okay, so this could be something like 12 factorial divided by 12 minus 3 factorial, which is 8 factorial, times 3 factorial. Oh, sorry, 12 minus 3, which is 9 factorial, times 3 factorial. Okay. Next, we want to see the number of ways to choose, this time the green marbles. Okay. Choose how many green marbles is the question asking? 2 green marbles. 2 green marbles from 8 green marbles. Now by definition, it is 8 choose 2. Right, again by definition. Now what can 8 choose 2 be written as? 8 factorial divided by 8 minus 2, which is 6 factorial times 2 factorial. Correct? So now what do we do? The question is asking how many ways can 3 black marbles and 2 green marbles be chosen? We know those how to count those events separately. How do we combine them? We use either the sum rule, okay, or the product rule. So think for a moment, should we use the sum rule or the product rule? So the answer is that we use the product rule because there is an and here, okay, and since there is an and, we should be using the product rule. If it's a 3 black marbles or 2 green marbles, then we should be using the sum rule. Okay, good. Now we know what rule to use. So let us just simply use that rule. So, right, so so by, okay, so number of ways to choose 2 green marbles, 2 green and how many black? 3 black marbles is nothing but 12 choose 3 times 8 choose 2, which we know to be 12 factorial by 9 factorial times 3 factorial times 8 factorial by 6 factorial times 2 factorial. So now what do we have? This is nothing but 12 times 11 times 10 times 9 factorial divided by 9 factorial times 3 factorial is 3 times 2 times 1. Okay. Times 8 factorial is 8 times 7 times 6 factorial divided by 6 factorial times 2 factorial is 2. So let me cancel out the 9 factorial here with the 9 factorial here. Let me cancel out 6 factorial here with 6 factorial there. Okay. Now any other cancellations possible? So 3 times 2 is 6, right? So 6 times 2 is 12. Okay. Now 2 times 4 is 8. So what do we have? 220 times 4 times 7, okay, is 28. So 220 times 28. So what is the answer of 220 times 28? It is 6160. So this is the answer. Okay. So let us move on. The question says, a club consists of 20 members, of which 9 are male, okay, and 11 are female. Okay. Club consists of 20 members, of which 9 are male and 11 are female. 7 members will be selected to form an event planning committee. Okay, so let me write those things. 20 members, total number members equals 20, okay, of which 9 are male and 11 are female. Then what does the question says? 7 members will be selected, okay. Need to select 7 members from here. and I could do it in several forms. Okay, I could choose all 7 from 9 or all 7 from 11 or some combination of both. But what does the question say? The question says, uh, how many committees of 4 females and 3 males before? I want to specifically pick 4 females, 4 from the 11 females, and 3 from 4 from here, and 3 from here. Okay, in how many ways can I do that? Now, again, the question to ask first, okay, would be: is this a permutation problem or is it a combination problem? Okay, the fact that I only need to choose, okay, the set of females, and I don't want to arrange them. I just want to choose the set of males, and I don't want to arrange them, okay, in whatever order. So I don't care about the order. This is a combination problem. Got it? So now the plan is simple. We just want to break them into different events. Let us look at the first event. Number of ways to choose 4 females from 11 females. It is nothing but 11 choose 4. Similarly, number of ways to choose 3 males from how many? 9 males is equal to 9 choose 3 by definition. Right? By definition. So again, now we need to combine these two. Now, looking at this question, think about whether we need to use the sum rule or the product rule. Now, this is similar to the previous question. Similar to the previous question, since there is an and here, okay, we should be using the product rule. So, number of ways to choose 4 females and 9 males is equal to 11 choose 4 times 9 choose 3. Getting it? Now we can simplify this as 11 factorial divided by 11 minus 4, that would be 7 factorial times 4 factorial times 9 factorial divided by 9 minus 3 is 6 factorial times 3 factorial. Okay, now let us simplify this further, which is equal to 11 times 10 times 9 times 8 times 7 factorial divided by 7 factorial times 4 factorial. Okay, so 4 can be written, 4 factorial can be written as 4 times 3 times 2 times 1. Okay, times 9 times 8 times 7 times 6 factorial divided by 6 factorial times 3 factorial. Now I'll cancel off the 7 factorial here with the 7 factorial there, 6 factorial here with the 6 factorial there. Now 3 factorial can be rewritten as 6 here. Okay, so what can we cancel out? So 4 times 2 is 8 here, right? So 3 times 2 is 6, 3 times 3 is 9. Now 2 times 4 is 8. Okay. Next, 3 times 3 is 9. Okay. And let me cancel this 2 with that 2. Okay. Good. So now the answer is 3 times 2 is 6. 6 times 11 is 66. And 66 times 10 is 660. Okay. Times 3 times 2 is 6. 6 times 7 is 42. 660 times 42, and if you compute this answer, it becomes 27720. So there are 27,720 ways to do it. Quite a large number. Okay. Okay, now let us continue with other problems. So this problem is based on words, or sometimes called strings. So the question is as follows: how many words can be made from rearrangements, okay, of the letters of the word bookkeeper? Okay. So what does this mean? If this is my word, okay, if this is my word, then what I do is I want to rearrange them. What I mean by rearranging is I bring B here, I bring O here, and I bring another O here, K here, and so on, and E here. Okay. So this is what is called a rearrangement. Now the first question I ask you is this a permutation problem or a combination problem? So the answer is that it is a permutation problem. Why? Because it is asking about arrangement. Remember that permutation is always asking about arrangements, and combination is always asking about choices. So we are not just talking about choices here. We are talking about arranging the letters. So what are we arranging here? The question is, in a permutation sense, the question is asking, take a set of letters from here and rearrange them. Okay. But what is the size of the set of letters? Okay, first of all, what is the length of the string? Okay. Length, okay, total length equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. So that the total length is 10. So number of ways to rearrange any 10 letter or 10 elements, let's say, equals. So one way to think about it would be I pick out 10, okay, from a set of 10 objects, and then I rearrange them. So from 10 objects, I pick out 10, okay, which is nothing but 10 factorial. If you see, another way to view it would be like I have 10 places, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. I have 10 places, and there are 10 choices for the first place. Okay, there are 9 choices for the second place. There are 8 choices, and so on. So by the product rule, it becomes 10 times 9 times 8, and so on, which is nothing but 10 factorial. There is a second view to look at it. But now what I want to do is, I want to ask you a question. Are we done here? Is this the answer? So the answer is that we are not done yet. Okay, because remember that there are repetitions. Okay, there are repetitions. There are repetitions here. So for you and me, for the reader, this E and this E mean the same thing to me. They are not different things. But for this fellow here, the permutation, it will treat the this E, the first occurrence of E, and the second occurrence of E differently. So for so so if I have three E's here, right, and if I rearrange them to be and they have some letters in between, if I rearrange them this way, okay, with the same letters, let's say R P K B, R P K B, then they mean the same thing for me. This word means the same thing, and this word means the same thing. but the permutation counts for it. The permutation counts this also and counts this also. We do not want that, and this is what is called over counting. Okay, we want to get rid of the overcounting. So how do we get rid of the overcounting? We divide, okay, by the repetition, the factorial of the repetitions. For example, E occurs how many times? 3 times. And K occurs 2 times. O occurs 2 times. Then what do? We divide by their factorial. Okay. So answer equals 10 factorial divided by 3 factorial times 2 factorial times 2 factorial. This is for E, this is for K, this is for O. For the explanation, the deeper explanation of why we do this, you can refer to the lecture videos of NPTEL. Okay, so this is the answer, and you can further simplify it, and it should be quite a large number. So yeah, let us move on further. Okay, now another word problem, another string problem. The question says the following: in how many ways can the letters of the word combinatorics be arranged if all the vowels are always grouped together to form a contiguous block? Okay, so combinatorics. In how many ways can they be grouped together to form a contiguous block? In how many ways can they be arranged, okay, so that the vowels always form a contiguous block? Okay. Or in other words, contiguous block means that the vowels are always together. They don't have some consonant separating them. So think about this question. How could we solve it? First of all, the first question would always be: is this a permutation question or a combination question? Okay. Well, the question is asking for arrangement, okay, not just choosing. So therefore, it becomes a permutation block. The question. Uh, Permutation question. Okay. Okay, now we know that it is a permutation question. How do we tackle this question? There's a popular trick used here. Okay. What we do is we group all the vowels. Okay. Vowels here are uh, O, I, A. Okay, and I'm counting the repetitions also, mind you. O, I. This is my vowels. Okay. Next, what do? I look at the consonants, which is C, M, B, N, T, R, C, S. So here total length equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Total length equals 13. So this should add up to 13. 5 plus this should be 8. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So yeah, we found all the vowels, okay, and the consonants. Now what do? I treat this as a single letter or a single symbol. Okay. So, for example, I write OI as a single letter, and the remaining parts 3, 4, 5, 6, 7, 8. I can put, let's say, M here, B here, T here, R, C, and so on. Okay, M, S, and so on. Okay. Okay, where does S go? S goes here and so on. And now I find number of arrangements for this. Why? Because if I find the number of arrangement for this, vowels are guaranteed to be together. Right. So I mean, I just do not arrange the consonants also. I arrange the vowels also. So the vowels can also go here and there and so on. This set OI can also go here and there. Okay. So that is the idea. Now what do I do? After arranging them, okay. So first let us find the number of arrangements. Okay. So number of arrangements. Okay. Let me call this X. Okay. For X equals. Okay. So how many letters are there? Um, there are one, okay, 8 here, okay, plus 1 here. There are 9 letters, okay, 9 letters, okay. Number of arrangements are 9. Permutation P, okay, and you need to arrange them, all of them, okay. You don't make a choice from them. 9, which is nothing but 9 factorial. But are we done here? Now, this is similar to the previous question. We are not yet done because C and C have a repetition. Okay, so C can exist here also, here also. So since there is a letter which repeats 2 times, we need to divide by the factorial of the number of times it repeats. Divided by 2 factorial. This is for the repetition of C. Okay, good. Um, Now again, so is this a final answer? Is this 9 factorial? Sorry. Is this 9 factorial by 2 factorial the final answer? It is not the final answer because these vowels O, I, A, O, I may not always occur in that order, right? They are together, that we agree. But A could come front, A, I, A, O, I, A, O, I. Okay, could be, this can be rearranged into A, O, I, or I, O, A, O, I, and so on. So for this, I need to find the number of arrangements, okay, of vowels such that they are contiguous. Okay, so that is nothing but they can be arranged in 5 factorial or 5p5 many ways. But again, be careful here because even the vowels are repeating. So I is repeating 2 times and O is repeating 2 times. So this becomes 2 factorial times 2 factorial. Okay, which is okay. Let's keep it at this. So finally, we combine them. We combine what we know. So number of ways that vowels are together equals, okay, firstly this, okay, number of ways that they are together in this particular order, A, I, O, this um, O, I, A, O, I form, and then take care of the rearrangements. Okay, this is 9 factorial divided by 2 factorial times the rearrangements of the vowels themselves. Why are we using times? We are talking about an AND case here, okay, not an OR case. So by product rule, this is the case. So times 5 factorial divided by 2 factorial times 2 factorial. Okay. Yeah. So this is your answer. Now I shall look at the case. Okay. So yeah. So now we are done with basic countings. Okay, permutations and combinations. Now we'll talk about what is known as the binomial theorem. Right. So the binomial theorem talks about expansions of expressions which have two terms, x and y. So here, if you look, x plus y to the power n, okay, can be written as n choose 0 x to the n choose 1 x to the n minus 1, and n choose 2 n minus 2, and so on. Basically, it tells you for a particular term what are the coefficients or how many of those terms exist, okay, in the expansions. So, in a more compact form, this is how you can write it as summation j goes from 0 to n. Okay. Okay. N choose j, n minus j, y to the j. Okay. So this is nothing but when you expand the summation, you get this above expansion. Okay. So this is the binomial expansion. Okay. So now what you do is we want to find what is called the rth term. Okay. Observe that in the binomial expansion, here what is j? J is 0. Here what is j? J is 1, j is 2, and so on. So since it begins from 0, here j becomes n plus 1. Okay. So 1 till n plus 1 for this. So there are 0 to n plus 1. So if I write this as the first term, second term, third term, and so on, what will j for the rth term be? For rth term, j is nothing but r minus 1. For the first term, r is 0. For the second term, r is 1. And, for the first term, j is 0. Okay. For the second term, or r equals 2, okay, j is 1, and so on. So j is simply r minus 1, right? So it is simple to find the rth binomial coefficients. Okay. The rth term, okay, is nothing but, n choose r minus 1. The j is r minus 1. X to the n minus j. What is j for us? R minus 1. And y to the j. What is j for us? R minus 1. Okay. So yeah, that is how you would find the rth term. We will look at questions pertaining to this. Okay. Okay. Good. So the question says the following: find the fourth term from the end in the expansion of x cubed by 2 minus 2x squared whole to the power 9. Okay. I mean, one way to do it would be like keep expanding using the binomial expansion, but we know something more clever. We know how to find the rth term, right? Now my question would be, what is r here? Well, if you do not, if you are not very careful, then you would say, oh, r is equal to 4, but that is wrong. What is the question asking? The question is asking not the fourth term. The question is asking fourth term from the end in the expansion. Okay. So the expansion of x cube, the expansion of x cube by 2 minus 2 by x square whole to the 9 will be some term plus some term plus some term and so on. right? But we know that if this is the first term, this is the second term, and so on, it'll go till the 10th term only. That is n plus 1, right? Uh, Sorry, not n plus 1. Yeah, third term. Okay, this should, sorry, this should be n. Yeah. So, yeah, second term, third term, and so on until it goes till n plus 1 term, right? Because it goes from 0, since it starts from 0. That is the key idea. It goes to the 10th term. N is 9 here. Okay, N is 9 here. So what do we do now? So we keep counting backwards. Okay, this is the first term from the end. Now look at T9. This is the second term from the end. This is the 8th term from the end. Oh, sorry, this is the third term from the end. And this is the fourth term from the end. Fourth term from end. Okay, which is seventh term from left. Thus, R equals 7. Now it's simple from this point on, because R equals 7 and we already know how to find the Rth term. So we simply use the formula. By formula, okay, Rth term equals, and choose R minus 1, which is 6, okay, and n is 9, okay, and x to the n minus r minus 1. N is 9, r minus 1 is 6, so x to the 9 minus r minus 1, which is 6, y to the r minus 1, which is 6. Which is nothing but n choose 6, x to the 3, y to the 6. Now what is n choose 6? N choose 6 is nothing but 9 times, oh, okay, sorry. 9 factorial divided by 6 factorial times 9 minus 6 is 3 factorial, x cube y to the 6, which is 9, 8, 7, 6 factorial divided by 6 factorial times 6. Okay, this will cancel out, this will cancel out, x cube y to the 6, 3 times 2 is 6, 3 times 3 is 9, 2 times 1 is 2, and 2 times 4. So this becomes 3 4 are 12, 12 times 7 is 84, x cube y to the 6. This is my 7th term from the left and my 4th term from the end. Okay, good. Now let's move on further. The question says, find the term independent of x in the expansion of root x by root 3 plus root 3 by 2x square whole to the 10. Okay, we want to find the term independent of x. Now what does the term independent of x mean? Okay, independent of x means that term is not affected by x value of x. Okay, so for example, is x square y, is this independent of x? It is not independent of x, because when x equals 2, x square equals 4, and when x equals 3, x square equals 9, it will totally change the term, the value of the term. Okay, so this is not independent of x. But if you have something like 4x cube y by x square z xy, okay, or not xy, by x to the 5 z, x square z, let's say. Okay, then this term is independent of x. Why? Because I can cancel off this to 2, and this I can cancel off to 1, and I can cancel out to z, which is nothing but 4y, right? It's nothing but 4y. So there is no x in the term actually. So this is independent. In other words, term has x to the power 0. So this can be written as x to the power 0, right? So the only x in the term, okay, has the power 0. So now the question becomes simple. The question is simply asking, tell me which term it is, okay, that such that you know the power of x is 0. Now how do I find that? Let's say let such a term, okay, be the rth term. Okay, good. If it is the rth term, we know the formula for it. Then rth term, my formula is nothing but n choose r minus 1 times x to the n minus r minus 1 times y to the r minus 1. Okay, but we don't know r yet, we want to find the r. So which is n, okay, what is n for us? If you look, n is equal to 10. Now 10 choose r minus 1 x to the n minus okay, sorry, let's call it a and let's call it b. They are using x and y in the equation, right? So what is a for us? Root x by root 3. uh, Root x by root 3 whole to the power n minus r minus 1. Okay, and next we have b. What is b for us? B is root x root 3 by 2x square. Okay, whole power r minus 1. And here let me write the n as 10 because it's 10 for us. Okay, good. Next, what do we do? Let me expand these two. Okay, 10 choose r minus 1. So root x can be written as x to the power half. And let me put that 10 minus r minus 1 inside. Okay, and divided by root 3 whole to the power 10 minus r minus 1. Okay, next let's do root 3 to the power r minus 1 divided by 2x 2 times r minus 1. Okay, this is what I have here. Now I'm only interested in the x. Okay, so let me just keep this aside. Root 3 whole to the power r minus 1 divided by root 3 10 minus r minus 1. Okay, this I'm not very interested in. Okay, I'm only interested in x times, okay, 1 by 2 from here. Okay, now I can write this as, I can subtract their powers, right, because it's division. I can write it as x to the power 10 minus r minus 1 divided by 2 minus this power 2 r minus 1. Okay, good. But we know this term is independent of x. So x has power 0, and we see that the only x in this term is here. Okay, so this means that whatever the power of x is, this will be 0, right? So which means x to the 10 minus r minus 1 divided by 2 minus 2 times r minus 1 is nothing but x to the power 0. So now let me equate these two powers together. So 10 minus r minus 1 whole divided by 2 minus 2r minus 1 equals 0. Okay, so let me take the LCM. 10 minus r minus 1 minus 4 r minus 1 equals 0. So 10 equals 5 times r minus 1 and 5 times 2. Okay, which means 5 times 2 is 10, which means that r minus 1 equals 2. So r equals 2 plus 1, which is equal to 3. Thus, third term r equals 3 is independent of x. Okay, and please look through this carefully. This is slightly more challenging question. Okay, but the key idea is still as follows: we are asking to find the term which is independent of x, right? So how do I find the term independent of x? What does independent of x means? Independent of x means that that term does not depend on the value of x. That term does not depend on the value of x. Or we can say that x has a power 0. Now what do we do? Let us assume that the term is the rth term. Okay, and we know how to find the rth term using this formula. What we eventually arrive is this x power this. But we know that this is independent, so x has power 0. And so we equate the powers simply. This term, this 10 minus r minus 1 divided by 2 and so on will be equal to 0. And finally find r. So r equals 3. So the third term is independent of x. Okay. Good. Now we slightly look into the multinomial theorem. Okay. So let's say you want to choose some set of things one after the other. Okay. Let's say you want to yeah. So the example I gave previously was, if I have a committee which has travel as one option, transport as the other team, and food as the other team. Travel, transport, food, and there are 7 people. How many ways can I allocate them into these travel, transport, food, such that I need 3 people for travel, 2 for transport, and 2 for food? How many ways can I do that? So let's say I have 7 people. Let's say 1, 2, 3, 4, 5, 6, 7. Okay. How many ways can I choose? 3 for travel, 2 for transport. I can choose them this way. This is one way to do it. Another way would be like choose, these 2 for transport, these 2 for food, and this for travel. Travel, transport, food. Okay, and so on. I want to find how to pick those people. So the formula for such a case is this. It's quite simple. N factorial divided by N1 factorial. Okay, or in other words 3 for travel that I need to pick, and n2 factorial 2 for transport, and so on. Okay, the technical idea is that I choose set of n1 elements from n. From the remaining, let's say I pick 3 for travel. From the remaining, obviously, I'll choose the transport people, right? And I choose the transport people, and from the remaining, I'll choose the food people. Similarly, I choose n1 elements from n. From the remaining elements, that is n minus n1, I choose how many? N2 people. And from the remaining, okay, after I choose n2, what remains? N minus n1 minus n2. So from this, I choose n3, and then I from n1 n minus n1 minus n2 and so on, I choose nk elements. Okay, so like binomial expansion, okay, we have what is called multinomial expansion. Binomial expansion can only take care of expansions where inside brackets you have two terms. But here, what if you have several terms? Then we work with what is called the multinomial expansion. The multinomial expansion is straightforward. It's similar. It's a generalization of the binomial expansion. You go over n1, n2, and so on till nk, and then do the multinomial coefficient, and choose n1, comma n2, comma nk, which is nothing but the same thing. You choose n1 first, whatever remains n2 you choose, and so on. We have this formula, right? For that, we have this formula. So multinomial coefficients times x1 to the n1, x2 to the n2, and so on. So this is what is called the multinomial expansion. Okay. So now the first question. The question says you have 8 distinct pieces of food. You want to choose 3 for breakfast. Okay. 8 pieces of food. You want to choose 3 for breakfast, 2 for lunch, and 3 for dinner. In how many ways can you do that? Okay. Let's look at that. You have number of n equals 8. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's do the more straightforward way to tackle this. Okay, there are 8 pieces of food. You need to choose 3 for breakfast, 2 for lunch, and 3 for dinner. Okay, this is one particular choice. So how do you do this? Okay, for breakfast, what you can do, number of ways equals, you can choose 3 for breakfast from the 8 items, and meaning product from the remaining. How much remains? Since you chose 3 from 8, okay, you will do 8 minus 3, which is 5 products remaining. From those 5 foods, you will choose 2 for lunch. And even from that, you choose 3 for dinner. How many food remains? Only 3. 5 minus 2 is 3. From the remaining, you choose 3 for dinner. And this is your answer. So let us simplify it, which is nothing but 8 factorial divided by 8 minus 3, which is 5 factorial, times 3 factorial times 5 factorial divided by 5 minus 2 is 3 factorial times 2 factorial times 3 to 3 is 1. There's only one way to select 3 elements from 3 elements. Okay, good. So this becomes 8 times 7 times 6 times 5 factorial. You have 5 factorial here, and 3 factorial is nothing but 6 times 5 times 4 times 3 factorial divided by 3 factorial times 2. Okay, I'll cancel out this 5 factorial with this 5 factorial. I'll cancel out this 3 factorial with this 3 factorial. Okay, now I'll cancel out this 6 with this 6, and this becomes 7 times 8. Okay, let me cancel this 2 with this 8. This becomes 4. 7 4s are 28. 28 times 20 is 2 to the 16, 2 to the 4. 5, 560 is the answer. So this is one way to do it. Or I have a more straightforward way using multinomial coefficients. See that this question, okay, is no more different from the small example I showed you about the people. This transport, 3 travel, 2 transport, 2 food, right? Which is nothing but this choosing set of n1 elements from n, and choosing n2 from whatever remaining and so on. Okay, so it's not different from that. So what all I need to do now is the answer is okay, n choose n1 comma n2 comma n3, which is nothing but n is for us 8, choose n1, 3 comma 2 comma 3 for delivery. Right. So this is simply my answer. Or I can simplify it to verify 8 factorial divided by 3 factorial times 2 factorial times 3 factorial, which is equal to 8 times 7 times 6 times 5 times 4 times 3 factorial divided by 3 factorial times 2 times 6. I'll cancel this off, and let me cancel off 2 times 4 is it. Okay, good. Now 6 and 6 can be cancelled off. Okay, which is nothing but 4 times 7 is 28 times 5 times 4 is 20 divided by 1, which is again 560. Okay, 560. So we see that this formula of multinomial coefficients actually makes things much simpler. You don't need to imagine, taking out n1 elements and n2 elements and so on. So it's much more simpler. So yeah, let's look at another question. The question says, okay, what is the coefficient of x1 cube, x2 square, x3 to the 5 in the expansion of x1 plus x2 plus x3 equal to the 10? Okay, so what is the coefficient of this? So we'll look at multinomial expansion. Why? Because there are 3 terms within the bracket, so we cannot no more look at binomial expansion. So we look at the formula for multinomial expansion. The coefficient for x to the x1 to the n1, x2 to the n2, and x3 to the n3 is nothing but n choose n1 comma n2 comma n3. Right. So yeah, how do we handle this case? So coefficient is nothing but n choose n1 comma n2 comma n3. But n1 is 3 for us, n2 is 2 for us, and 3 is 5 for us. Right. So which is equal to what is n? 10 choose 3 comma 2 comma 5. Now we can simply use that simple formula that we have, which is nothing but 10 factorial divided by 3 factorial times 2 factorial times 5 factorial, which is equal to 10 times 9 times 8 times 7 times 6 times 5 factorial divided by 6 times 2 times 5 factorial, where I can cancel out this 5 factorial with this 5 factorial. Okay, this 6 with the 6. Okay, and let's say this 2 with this 8, 2 4 z. Okay, so which is equal to uh, so 40 times 63 is nothing but 60 is 18. Oh, sorry. For 3 is 12. 3 is 12. 1. 6 is 24. 2520 is your answer. Okay. Okay. Good. So we'll look at the final part of this session. Okay. So this is what is called, counting partitions. Okay. So this kind of problem is slightly different from. It is kind of similar, but still kind of different from the previous multinomial problem. Okay. In the previous multinomial problem, what did we ask? We said, okay, these are the set of objects. I want 3 people here, 2 people here, and 3 people here. How many ways can I do that? But let's say I already do not know the number of people I want in each team. I just want to, allocate them to those teams any way possible. Okay. So then I use this bars method, or sometimes also called stars and bars method. Okay. Here, what do I say? I have n objects. I need to partition them into k parts. So I have 8 objects. Okay, let's say these are the objects. Okay, and I need to partition them into 3 parts. So how can I partition them? This is one way to do it. Okay, or this is one way to do it. Or I'm also allowing empty partitions. Okay, this is another way to do it, and one is left empty. Okay, so how do I do this? My argument is that just give me 2 sticks, just give me 2 bars. Okay? Just give me 2 bars. It is enough to partition them, represent the partition. What do? I keep a bar here. Okay, let me show by a different color. So I keep a bar here, and I keep another bar here. Okay. So what would this mean? What would this mean? This means this is my first partition. This is my second partition. This is my third partition. Okay. 2 is enough to show. Let's say I keep the bar here and I keep the bar here. Okay. So what would this mean? This means 3 people here, 0 people in the second partition, and 5 people in the third partition. Okay. So how do I represent this? I just make, okay, k minus 1. I make n boxes. Okay. I make n boxes 1 2 3 4 5 6 7 8. Okay, n boxes, and k minus 1 more boxes to accommodate for the bars. Now if I put a bar here 1 2 3 4, and I put a bar here, okay, this is nothing but this is the same thing that this represents, right? And if I had put a bar here and put a bar here, it will represent what the previous scenario showed: 2 elements in the middle and 3 elements at the final partition. So what I want to say is, what I want to say is, okay, let me keep this for future reference here. See, what I want to say is that selecting the places for these k minus 1 bars in this n plus k minus 1 boxes, okay, n plus k minus 1 boxes isn't enough of an argument. Okay, it is enough to count these bars to count the number of partitions possible. I hope you are convinced now. Okay, so now that that is done, and how many ways are there to place these bars in those boxes? There are n plus k minus 1 many boxes, and there are k minus 1 many bars. So I just need to choose k minus 1 boxes. Okay, among n plus k minus 1 total number of boxes. That is my answer. Okay, good. So let us look at the first question. How many ways? Okay, how many ways can you buy 8 fruits? Okay, if your options are apples, bananas, pears, and oranges. How many ways can you buy 8 fruits if your options are apples, bananas, pears, and oranges? Okay, so you have, you know, 4 boxes, and you can only carry a total of 8 fruits. So let's say you put, you know, this is for apple, bananas, pears, orange. So let's say you put 4 apples, 3 apples here, okay, and 2 bananas, okay, here, and you have 3 more places, okay. So you take 2 pears and 1 orange. This is one way, or you could not take orange also. You can take 1 pear. So see that this is actually a partition problem. How is this a partition problem? I make spaces for, you know, I make these round things for to show fruits. This partition can be showed by these sticks, and none for oranges. 3 apples, 2 bananas, 3 pears, and 0 orange. 0 orange. Okay. So this is how I can simply represent them. Right. Now what I do is so number of uh, okay, 3 pairs, and okay, I just need this bar. No need to show the second bar. So how many number of bars needed equals 3. Okay, k minus 1, which is 3. Here what is n? N is 8. K is the number of partitions I need, that is 4. So 4 minus 1 is 3. So number of ways to pick the fruits is nothing but n choose n1 comma n2 comma, oh sorry, nothing but um, n minus whatever the formula there was for bars method, n plus k minus 1, choose k minus 1, which is 8 plus what is k minus 1, 3, choose 3, which is 8 plus 3 is 11, choose 3. Okay, what is this? It will be a huge number, so I can leave it at that. Okay, or if you oh, okay. So what I can do is I can simplify it still, and 11 factorial divided by 11 minus 3 is 7, not 7, 8, factorial times 3 factorial, which is 11 times 10 times 9 by 3 factorial, which is 6. 3 2s are 6, 3 3s are 9, 2 5s are 10, which is equal to 3 5s are 15 times 11. 15 times 11, which is equal to 165. Okay. Now we look at the final question of the lot. Okay. The question is as follows: how many solutions, okay, are there to the equation x1 plus x2 plus x3 equals 10, where x1, x2, x3 are non-negative integers? Now think about this question. Okay. One hint I can give you is use the bars method. So you must somehow think of what elements you should use and what the partitioning will be. So the idea is as follows. At the end, you want the sum to be equal to 10. Okay. At the end, you want the sum to be equal to 10. And 10 can be written as 10 ones. That is the 1 plus 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 1. Can be written as a sequence of 10 ones. Okay. This is equal to 10. Now all you have to do now is partition these ones. Okay. Let's say this is the first partition, this is the third partition, and this is the fourth partition. x1, this is my x1, this is my x2, this is my x3. So what is this? x1 equals 2, x2 equals 3, and x3 equals 5. And similarly, I can partition them into different ways, right? And so, what is my number of partitions? Number of partitions is 3. Number of bars needed will be 3 minus 1, which is equal to 2. Okay. So I need just 2 bars to do this. And this again now becomes a partition problem. Number of solutions equals what was the formula for the bars method? N minus k minus 1. Choose k minus 1. It's nothing but what is n? 10. Choose. Okay, there are 10 ones out here, 10 elements here. Okay, out of minus you use 2 sticks, 2 bars. Choose 2, which is 8. Choose 2, which is equal to 8. Okay, factorial divided by 8 minus 2, that is 6 factorial times 2 factorial. Okay, which is 8 times 7 times 6 factorial divided by 6 factorial times 2. So you cancel this. Okay. Plus 2 is 8. Yeah. Okay. So 7 8s are 56 divided by 2 is equal to 2 times so 25, 28. 28 is the answer. Okay. Okay. So yeah, so we've come to the end of the session. That is all that I will discuss. So please go through the video. If you have any doubts, please pause and go back to it once again. This was about the week 1 session. The week two session will be happening for me, okay, on Tuesday at 6 p.m. to 8 p.m. Okay, and the content for week two would be set theory. So it is an interesting topic. I hope that I can clear all your doubts there, and hope to see you there on Tuesday 6 p.m. Okay, thank you.